Good morning, everyone. How's it going? This is Gad, and this is another video for continuing our learning journey. As you see, I did manage to do a cover photo for my channel. That's nice. Well, as we left before yesterday, we finished the basics, and I till now I did not finish this. I was doing other stuff, other boring stuff. I was trying to learn cryptography. Yeah, I don't know why. Have no idea. I do enjoy cybersecurity. Yeah, I don't want to be a hacker, but I don't know why I'm doing it. So yeah, I don't care. Whatever. So I did some cryptography, crypto. Yeah, yesterday. Yeah, is yesterday in French. Sorry. So so I'm closing this. So in this session I will try to do this in approximately 2 hours. I will try to finish this in 2 hours, and maybe tonight I will do this. I didn't see how much videos are inside actually. So today we're going to do this simple algorithm. No, maybe I'm mistaken. It's not simple algorithm. Yeah, it's simple algorithm. Yeah. So the second. Oh yeah, that's long. Yeah, maybe tonight. I will try it in the night. Yeah, I'm trying to do everything in the weekend, so I don't have lots of time to prepare myself. So as we say, our YouTube, our course page, my Google Translate, and the page here, and Sublime text for editing script, Python script. This is the Python script that we did it yesterday, about the last video yesterday. I don't yeah, the last video. I'm going to delete it. I don't want to keep it. I think we're good. And yeah, as usual, not sharing the content of the questions below here. Sorry, you have to do it on your own. And yeah, let's roll. I have my notebook here. I'm going to take notes as usual, so let's hit it. Hope you enjoy, guys.
We added looping variants. We had for loops, we had while loops.
Hi.
In the last lecture, we added looping variants. We had for loops, we had while loops, we had the notion of iteration. We used that to start generating some examples of guess and check algorithms.
So I hope the sound is good.
In this lecture, we're going to go back to that idea, but extend it, and we're going to add in another kind of data type, a string. We talked about it a little bit earlier on, but we're going to use it to actually look at ways to generate algorithms that can start to do some more interesting kinds of things. Just to review, I want to remind you what we did inside of loops. Here's an example of some code that's going to compute a square root of something. And it does it by running through a loop. As we've done before, it's going to set up an initial value, which it gets here by inputting something that enters an integer. And then it's going to run through a little while loop. Where
Yeah,
it does
I do think my internet connection is very bad today. I don't know why. I'm having problem about connections, and like there is really problem. Like my Facebook page is not reloading, so that does suck. Well, we'll try to do it. If I have if I had a lot of problems, I will change it to my 4G connection.
guess and check. He keeps trying different versions of answers, starting at 0, then 1, then 2, going on until it sees whether that answer squared is bigger than or equal to x. Once it gets to that point, it checks to see if it's actually the square is equal to x, in which case it prints out that it's found the cube root. And if not, it tells me that it's not a perfect cube, And just depending on whether it was a positive or negative thing, it gives me a little bit of additional info.
Okay. So maybe did we do this yesterday? I think we did.
And just
Yeah. Let me check because can I do Ctrl Z? So this is for trying to. No, this is not the square root. So this is the square root of. Okay. Now I'm going to delete this. And here. Do we? You think we can do this? Let's give it a try. Let's give it a try.
he keeps trying different. And then it's going to run through a little while loop where it does set up and initially some more interesting kinds of things. We did inside of loop.
Yeah, let's hit it. Yeah, let's go. Let's go. So it's a Python script. Yeah, it's a Python script. So answer is 0, next flag is false, x equals to integer input. So let's try my answer equals to 0 and make flag let's say flag. Yeah, I don't see the point of flag 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 equals to false, and false have to be big letter, big case letter, capital letter. The F have to be capital letter. I don't know why. It's just Python shit. Input. So enter integer. And I'm going to integer integer. No. And then this is how it's going to be clean. Nice. Let's do this, and then let's do this. Yeah. Okay, that's nice. So if we have if x is smaller than 0, well, that means, yeah, that's a degree expression. No. So flag is true, and true here is the same. True is the same case with false. Capital letter T. Have to be careful. So yeah, while here while is going to be yeah, I don't think so. So got shift tab, enter. So it's a while loop. While my answer the square root of my answer is less than x, then my answer my answer equals to my answer plus 1. And actually, yeah, I'm going to do it like this. Yeah, so this is exactly the same thing. This laid for the same of this. So okay, so we can go out from the for loop also, while loop, and we have another loop. Let's do some spaces between them. If my answer. Yeah, my answer. Why it's not working? My answer. If my answer, if the square root of my answer were x, were x, then print square root of x is yeah. So I'm going to do it just like square root of x square root of yeah, I'm going to do right square root of no, I'm going to keep this because the spaces here, I think they will be a problem. So I'm going to do this space x semicolon is, and I don't think I need to, yeah, colon space my answer. Else, so we have else here, print print x, yeah, is not, I'm not going to do a space, no, yeah, I'm going to do a space, yeah, is not perfect square, yeah, perfect square. And there is an if statement inside the if, the conditional if original conditional if statement that says if my flag, that mean if it was false, print just checking, did your main minus x, did you mean minus x? Ha ha. Yeah, okay, I did understand it. So we are checking if it's not the same, because we already eliminate all the possibilities there except the negative, except of no, how did we, what is this? Well, I don't understand. Yeah, let's see the video.
Here's an example of some code that's going to compute a square root of something. And it does it by running through a loop. As we've done before, it's going to set up an initial value, which it gets here by inputting something that enters an integer. And then it's going to run through a little while loop where it does guess and check. It keeps trying different versions of answers, starting at 0, then 1, then 2, going on until it sees whether that answer squared is bigger than or equal to x. Once it gets to that point, it checks to see if it's actually the square is equal to x, in which case it prints out that it's found the cube root. And if not, it tells me that it's not a perfect cube. And just depending on whether it was a positive or negative thing, it gives me a little bit of additional information. You can look through the code. I'm not going to run it. What I want you to check, I generate, and just depending on whether it was a positive or negative thing, it gives me a little bit of additional information.
Haha. Yeah, because here Yeah, because it could be a square root. It could be a square root, but the problem is we are not seeing it. For example, minus 16 um, could be the square root of 4, but of minus 4. So no, how fuck. Actually, if we did, if it's minus 16, could be. Uh, we can add a minus before it, so it will be. So it's just a negative, positive things, but not the integer itself. Yeah, okay, okay. But we are converting it to integer. Yeah, it's yeah. I did get it. So let's run the script actually. So if flag, that means flag is false. Okay, that means flag is false. Yeah, print. Just checking. Check. Yeah, that's checking. I don't know how to do that checking. CKING. And do you mean minus x? Let's do this minus x semicolon, and let's do space, and that's this. And let's see, enter an integer. So 16. Yeah, Sublime Text don't work with inputs. Ah, that's bad. So let's check out where we VS Code, VC Code. I hope it will run today. What is happening? How? Yeah, because it opened the same folder. Yeah, okay. So run it. 16. Square root of 16 is yeah, 4. Let's run it again to do 21. 21 is not perfect square. Trace back, line 16, if flag. Yeah, flag here is they have run it. 21. Shit. 21 is not square root. Okay, so let's take the case of minus 16. Ha ha ha. Ha. How do we say the flag will be false? Uh-huh. Minus 4. I don't want to do minus 4. I don't want to do minus 4. I will do minus 21. It's not square root. Okay. Well, actually, it have to print this. Why it's not printing this? Why it's not bring? Am I missing something? No, stop, please. Am I missing something here? Am I missing something? Am I missing something? Haha. Why it's not printing this? Well, it's not. It's not, it's not, it's not, it's not, it's not, it's not. Print X is not perfect square. He did print is not. And why you're doing this to me? Why are you doing this to me? Why are you doing this to me? I don't know, guys. Actually, I'd have to print this last, the last one. It's not printing it actually. See, because it's not. So it's less than 0. Ah, so let's try 0. Let's try 0. Okay. 0. No. Shit. What we didn't try before? So enter an integer. So actually this is not going to work because it's not an integer. Trace back. Yeah. But this is not. What's the problem? What is the problem? What is the problem? The problem. What is it? Ha ha. So I'm going to pause the video to find the solution, I think. Yeah, so I did not find any solution actually. So what type of integers we can put? Because the problem is that we have to choose something have no square root to pass in this if flag. So what is it? If flag? Well, I just don't get it. If flag, that mean this is have to be false. So I it's a simple math. I don't get it. Yeah, I don't care.
And just depending on whether it was a positive or negative thing, it gives me a little bit of additional information. You can look through the code. I'm not going to run it. What I want you to see is that idea of guess and check. I generate values for answer until I get to a point where either I'm done and I have the answer or I've gone too far. And again, as before, I've got something where I'm setting up the variable outside and I'm changing the variable inside with a test that depends on it. We're going to use that idea as we generalize, but I want to remind you of what loops do. And as before, I don't need to do that actual version of answer equal answer plus 1. I could use plus equal as a variation of it. We also talked about strings earlier, and I just want to remind you of those because we're going to use them in this lecture as well. Think of strings as a sequence of characters. In fact, case-sensitive characters. For letters, could be lowercase or uppercase. As with numbers, I can compare them. I can say if two strings are equal by using the double equal sign. I can use greater than or less than, using lexicographic order to decide if two strings are greater than or less than each other. Length can give me the number of things in the string. And as we saw before, we can use square brackets to do indexing into a string. We can get the 0th element. Remember, it starts at 0. The first element, the second element. And if I have a string 3 long and I try and get something 3 or bigger, it's going to complain, telling me that I've tried to access beyond the end of the string. We also saw slicing in strings. This lets us go into a string and pull out pieces of the string. And here we saw we can specify a start point, a stop point, and how many steps to take as we do the accessing. And that lets us pull out different elements out of a string. One unusual thing we haven't seen before is if the step is -1, we actually access the string in reverse order. There it is right there. Otherwise, if we say, for example, start with the element 3, it says 0, 0, 1, 2, 3. So I start here, and I stop just before the 6th one. So 3, 4, 5. I'm going to pull that out, which gives me the piece that I wanted there. One last thing about strings is that they are what we call an immutable type. You can't change them. They can't be modified. And to see that, let me do a little example. I've shown it on the slide, but let me actually type it in over here. I'm going to define the string S to be, I'm going to define the name S to be the string hello. If I print out S, it gives me back. If I say what's the type of S, it tells me that it's a string, which is great. I can certainly index it by saying, give me the 0th element of S. But if I wanted to change the 0th element of S, for example, saying, I want to have the 0th element of S be the character Y, it's going to complain. I can't go in and change a piece of S. We're going to see other structures where we can do that are called mutable. Strings are not. I can't say, I want the 0th element of S to be Y. I can change it, but I have to redefine S. So I could say, let S be the character Y plus the rest of S starting at 1. And I could, in fact, say until I get to the length of S, or I can just say 1 all the way on to the end. And now, if I look at S, it's yellow. Misspelled for yellow. Point is, I've now changed the definition for S. So I can't change it individually. I have to redefine S. And that's why I say strings are immutable. One of the things I would suggest to you is if you're not sure what a command does, look it up or try it out yourself. That'll give you a sense of the different things you can do with strings as you move along.
I'm taking notes, guys.
And here, just to remind you, S was initially bound to hello. When I do the last call, I'm changing that binding and redefining it to be a changed new version of a string. The original string is still stuck in memory. It's just floating around. I can't access it anymore. Finally, remember for loops, a quick recap. We have that idea of having a loop variable that iterates over a set of values. And we can either do that with simple things like the range shown here, which is going to go from 0 up to 4, but I could also do it starting at 4, going up to 8. Expressions inside the loop are going to be executed for each value of the variable that I use. And so range is a nice way to iterate over numbers, but a for loop variable can iterate over any
Yeah, my internet is very
set of
bad.
values, not just numbers. And so, for
Wait,
example,
stop. Go
I
back.
could loop over each value of the variable that I use. And so range is a nice way to iterate over numbers, but a for loop variable can iterate over any set
Please
of
stop.
values, not just numbers. And so, for example, I could loop over strings. That sounds kind of neat. So here's a simple little piece of code. I've defined S to be a string, the first set of letters in the alphabet. And I can now write a for loop that says loop for the index over the range of the length.
Yeah, let's try to code this. Sublime, sublime. I don't know. Do I keep this to verify? No, I'm going to keep it. Let's code this. So, well, actually, no, I'm not going to code this. I don't know. No, yeah, no.
The best. Well, that's a lot of words. Let's say it a little bit better. It says, I'm going to see how long is S, and then I'm going to use range to generate the integers from 0 up to S, the length of S minus 1. I'm going to call that index, and then I could run through a loop that says if the element of S at that point is either an I or a U, I'm going to print out a little piece of information. No big deal. That just looks like a normal loop over integers. But I could also write it this way. I could say loop for character.
Ah, my resolution is really bad. Why? So I'm going. I think I'm going to pause, so I can change to my. Another Wi-Fi. Yeah. No, I'm going to do it right now, so I don't need to pause. So right and right. I'm trying to find my Wi-Fi actually. Where are you? So Android is connected. Connected. Yes. So we are on 6:47:45. Refresh.
For character in
Yes.
a little piece
Yes.
of information. No big deal. That just looks like a normal loop.
It's better now. No.
For integers. But I could also write it this way. I could say loop for character in S. And that's kind of cool. S is something we call an iterable. It says I can actually write a loop that lets characters start with the first element of S, and then the second element of S, and then the third element of S, doing the same kind of test as I move along. And it will do this until it runs out of characters in S, in which case it will execute, or exit from the loop rather, and move on to other kinds of things. That second piece of code is much cleaner. It's easier to see what I'm doing. I'm looping for all the characters in a string, as opposed to saying I'm looping for an index over all the indices into the string. And that's one of the nice things about both strings and especially about loops. I can iterate over anything where I can successively enumerate each of the elements of that piece. So now I've got strings as something which I can use as parts of loops, and that's really nice. Let me give you one last example, sort of a fun example. I'm going to set up a little loop that is going to run over basically a set of words. And what is it going to do inside of here? I got a little while loop here that says as long as, rephrase it. I'm going to input a word based on some input I give there. And what it's going to do is it's going to loop over all of the things inside of the word, basically saying if the character in the word is in a special set of characters. I'm going to print out something based on that. If it's not, I'm going to print out something different based on that. And then I'm going to increment I, and I'm going to keep going. So again, it's a while loop, but I'm using the character inside there to loop over particular elements of a string. Let's see what this does. So here's the code, and if I load it into my environment, it says, I'm going to cheer for you. Give me a word. So we'll give it the best word I know, which is, let me just get it over here, which is MIT. And it says, how enthusiastic are you about MIT? Well, I like MIT a lot, so I'm going to give it a 10 out of 10. And it says, I'm not going to repeat it all, but give me an M. M, give me an I, give me a T. T, what is it spelled? And it prints it all out. All right, it's a lame example, but you know what? I'm from MIT, I like it. What I want you to see is how I'm looping over, especially here, in this place right in here. I'm using the loop over a set of strings in order to be able to decide what I'm going to do. And why am I doing that? Because if it's something that is a vowel, I don't want to say, give me a. I want to say, give me an A. If it's something like an M that we pronounce that way, I want to say, give me an M. Whereas in the other cases, I want to say, just give me a C, give me a D. Okay, cute example, key point. I've now got two different loops going on here. The outer one is walking through each of the elements of the word. That's this one right here. And that's just doing the standard thing where I've set an iteration variable outside, right there. I'm changing it inside the loop. But in the loop, I've got another one, which is right here where I'm looping over all of the elements of a string. I can do it either way, and that works out really well. On that cheery note, we're going to move on to another topic.
All right then. Yeah, I don't want to do more for loops. Next video. Let's go.
And check algorithms to solve some simple numerical problems. But if you think about it, they've all been doing things with integers, where there is a finite number of choices that we have to check. And that makes sense. I can certainly run through all of them until I get to either the right answer or determine there isn't a possible answer. But now suppose we want to find, say, the square root or the cube root of any non-negative number. It could be an integer, it could be a float, it could be any number. I can't generate all possible guesses. They're infinite. So I can't, in this case, guarantee an exact answer, but I could come close. Now what I just want to do is try and find a guess that's close enough to the cube root or the square root of the thing I'm looking for. I can still use that notion of exhaustive enumeration, but I'm going to now have to pick examples where I take small steps in order to generate the guess and check to see if I'm close enough. Let's see what that might look like. Here the idea is I have to define what's a good enough solution. So I'm going to start with a guess, say 1. I'm going to check to see if that's close enough. If it isn't, I'm going to change it by a tiny amount, say 1.001. Check that one, and then 1.002, and keep doing that. So I need to increment by some small value as I go along. But I also have to define what does it mean to get close enough. It won't be exactly the same because I'm not going to be able to guarantee that. So here I'm going to use, in the case of cube root, something that tells me whether I'm close enough. By looking at the guess cubed, take the absolute value in case it's negative, and look at the difference between that and cubed to see if it's less than or equal to a small number. And if it is, I'm going to say I'm close enough, and I'm going to stop. One of the tricks here is that when I have these small values, I'm going to have to be careful. If I make them really small, I'll make sure I find a really good guess, but it's going to slow the program down. If I make them really large, I might actually miss the answer. And similarly, when I decide how close I want to get with epsilon, if I make epsilon big, I'm going to make it easier to find an answer, but I might get a less accurate answer. And so I have to think carefully about how I do both of those. But let's look at that idea to see how I can still use the idea of guess and check, but now with things that could compute the cube root of anything. So here's an example. I'm going to start off with some value for the thing I'm trying to find the cube of. 27 is going to be an easy one. I'm going to set up some initial values. Epsilon is going to be something that tells me how close I want to get to the answer. Guess is where I'm going to start. And increments the size in which I'm going to increase my guess as I move along. And just to keep track of it, I'm going to set up another variable called number of guesses. I'm going to use that to keep track of how many times do I go through the loop as I do this. And then what does this code do? It says while the difference between the cube or the guess cubed and the thing I'm trying to find the cube root of, while that difference is still bigger than epsilon, I'm going to keep going by incrementing guess by increment. There's that plus equal that I've used before. And changing number of guesses by 1, saying I've done another guess and keep going. I'm going to keep doing that until I get to something where the difference between guess cubed and cube is small enough. And at that point, I'm going to stop, and I'm going to return both how many guesses did I run and some information about did I find the right answer. Let's see what happens if I run that. So there's a piece of code. Let me start with 27, which is the thing I had before. And if I load that and run it, it gives me, not quite the answer I expected. It says 2.9970000001906 is close to the cube root of 27. And that's true. We're going to see in a little bit why it doesn't just give me 3. It gives me this funny answer in there. But you can also see that it took almost 30,000 times through the loop before it got to that. Why? Because I started with a very simple answer, 0. That wasn't close enough. Then I went to 0.0001, then to 0.0002. And you can see I'm going to have to do a lot of things until I get to something that's going to give me a good guess. Now, I could pick another example. Let's make it 29, which I know is not a cube root. Let's see what happens if I do that. It's not a perfect cube, but in this case, it found it. That's actually nice. In the previous case, I could only find things that were cube roots of integers. Now I've got something where the cube root isn't an integer, but I can still find it. This took almost 31,000 times through the loop. So I could say, you know what? I want to use something where I'm going to step a little more broadly. Let's step every thousandth of a step rather than every 10,000th of a step. And now if I run it, okay, I get a little bit different guess, but it only took 3,000 trials through it. And if I change it to say the increment should be in hundreds, you can run that. And if I do that,
Just the 30,000 operation.
It didn't like that.
Dude.
Think about why it didn't like that. What's happened here? It's off in an infinite loop. And the reason it's off in an infinite loop is because I'm checking only to see if I get to a place where it's close enough. I've actually gone right past the cube root and it's still running. So I need to stop this and I'm going to interrupt it to hold it back. That's something I need to fix. So if I go back to a little bit better increment here and rerun it, I get back to the thing I wanted to have. Okay, how would I fix that? I need to make sure that the guess isn't too big. If you think, and I'm going to go back to where I was. With this test, it simply says when guess cube minus cube, as long as it's bigger than epsilon, I'm going to keep going through the loop. If my step is too big, I could try something just below cube, but not have it work, and then go past cube and keep going further and further on. That means says I need to make a change here, so I want to make sure that my guess is still small enough. And if I make that small change, which I'm going to do over here, and guess less than or equal to cube, I should be in a little bit better shape. I can still run the same one, but now if I change increment to tenths, run that, it gave me a solution. Not a very good one. It basically says I didn't find a solution, but at least I didn't keep running forever. What was the point of doing this? It's not to try and trick you. It's to remind you that as you make changes to the code, you need to think about the consequences. And this was one where my test wasn't capturing all of the cases. So what can I say about this particular algorithm? The step could be any small number. If it's too small, it's going to take a long time. But as we just saw, if it's too large and I'm not careful, it could skip over the answer without getting close enough. At least in this case, I stopped rather than running forever.
So there is an imbalance.
In general, it's going to take x divided by step number of times through the code to find a solution. And so clearly as I make steps smaller and smaller, it's going to increase the number of steps, and I'd like to find a more efficient way to solving this problem.
Okay. Well, actually, it was more theoretical. Yeah, okay. It were more theoretical.
Exhaustive algorithms, guess and check algorithms. When we got integers, we saw that's nice because there's only going to be a finite number of solutions, but we won't be able to find, say, square roots or cube roots of numbers where that isn't a perfect square or perfect cube. We've generalized that to look at something that does a different kind of guess and check, where we take incremental steps, still enumerating all the possibilities within the resolution of that step, trying to find a solution. And we saw that that either means we take very small steps and we take a long time, or if we take larger steps, we might miss the solution. And I suggested we want to find a more effective way of doing that. So here's an example of that, and a wonderful tool that we're going to see a lot as we go through the course. It's called bisection search. Let's think about square root. One of the things we know about the square root of a number is that it lies between 1 and that number, if that number is bigger than or equal to 1. We'll do fractions in a second. So square root of 25 lies somewhere we know between 1 and 25. Here's the basic idea. Rather than trying everything starting at 1 and taking small steps, suppose we pick a number in the middle between 1 and, say, 25, 12 and a half. If we're lucky, that's going to be close enough. Now, it's probably not close enough in this case. We know where it is, but it's a nice start. But we can take that idea and generalize it. If it's not close enough, then we can ask, well, was the guess too big or too small? And in particular...
So I'm just going to take some notes very fast. Yeah.
But we can take that idea and generalize it. If it's not close enough, then we can ask, well, was the guess too big or too small? And in particular, if that guess g squared is bigger than x, we know it's too big. So what can we say? Well, we know that the answer has to lie below g. And that's really cool, because it says all of this stuff here, throw it away. I don't have to look there. I know that the answer has to be somewhere between 1 and g. Do the same thing. Pick something halfway between. That's my new guess. Try it again. If it's close enough, I'm done. If it's not, ask the same question. And for example, in this case, if g squared is less than x, then we know it's too small. So we can throw that stuff away and only focus on this portion. And again, pick something in the middle and keep trying. You can already see why this is going to be really nice, because on each step, I'm throwing away half of the things that I don't have to look at anymore. And that's going to let me hopefully very quickly zero in on finding the right solution. That's a wonderful idea. It's called bisection search, and we're going to use it. So, what did we say? At each stage, I'm losing half the values. Really cool. Let's see what happens if we wanted to actually make code for it.
Before making code, I'm going just to finish writing some notes. Okay.
What happens if we wanted to actually make code? So this is a little bit of a busy slide, but we'll walk through it. This is an example of computing square root using that example of bisection search. I'm going to start off just giving it the thing I'm going to look for. X will be 25. That's the thing I'm going to use as the root. Again, I'm going to pick something that I'm going to use to tell how close I am. And I'm also going to keep track of how often do I actually run through the loop, just to compare it to what we saw earlier. I need to set a low value and a high value, the range in which I'm going to look. Initially, that is 1.
I'm going to code it.
To the
I'm going to code this, but I'm waiting to see him explain the code.
Root, sorry, to the number itself. And then I'm going to make an initial guess, just halfway in between. Just high plus low divided by 2. And then I run through one of those nice little loops. What do? I say, if the difference between the answer squared and x is bigger than or equal to epsilon, I'm not close enough. And in that case, I'm going to print out some information, increase the number of guesses by 1, and then do what I just did, which is if answer is too small, that is, if answer squared is less than x, then I can change the low part of the range to move up to answer. And if answer is too big, I can change the high part of the range down to answer. As I did before, I start out here, If answer was too big, I change the high range to bring it down into there. If answer is too small, I bring the low range down into there, and I keep sorting it down until I get into something that's reasonable. This algorithm just captured that idea I just described. So let's try it out. We'll do it with 20.
So let's code it. Let's code it. Actually I'm afraid to code it because I do think it's hard to code. Yeah. Okay. So let's do here. No, here. So we have four variables, and five. I have five variables, so I'm going to name them as I want. I'm going to start with x. X equals 250. Epsilon, I don't know what this is. Epsilon, what does it mean? Epsilon. Yeah, I'm going to eps 0.01. Name guess. I'm going to guess. Oh no, it's SS. Guesses equals to 0. High or low, high, ash please, is x, and low is 1.0. And my answer equals to high plus low divided by 2.0. Okay. High plus low. That's not low. And divided by 2.0. So this is our variables. So now he's taking the absolute value of square root minus so the square root of the sum of this and this. So wait. So this is the middle. Previously he's trying to find the value which abstract he square it, and he took what? Did he square root the highest and the lowest value and took 25 from it and divided by 2 and more. So he want to check that the value in the middle, that the half of this value is not the square root. It's like 4. If you make 4, so the middle half of 4 is 2. So 2 square root of 2 is is uh, is 4. So he's taking out 2. So if it's equals to this, because this is a conventional value, this value is very small. So this is the difference. Well, he's going to say this is the square root. Okay, now I understand it. So actually now, yeah, this is the first example. If he took a value and this is okay, nice. Y, we're going to take the absolute value of the square root of my answer. Minus 2 minus x, which the number less or equals IPSEC, ABS. I don't know what it's ABS, so I choose ABS. So if it's like this, print this is it. Low sudo, no, I'm going to try to print this is the square root of this is the square root of x, and we're going to write my answer, I think. Yeah, he's going to take it like as a string. He's going to take it as a string. Well, let's write my answer. And he's increasing the just to find the guesses. Plus 1. Nice. It's increasing the counter. So now he is going to check if if my answer does not, the square root of my answer is less than x, low is my answer. Low equals my answer. Because we are going to replace this with the value that we choose. Now, so else, if it's more than so if it's if it's more, we replace we're going to replace the value of x with the highest Yeah, well, so it's x. Okay, nice. So the high equals my answer. And we're in the same while loop, answer equals yeah what did just I yeah answer equals parentheses high gosh, I think but yeah it's I plus loop divided by 2.0, so it's a float value. I'm going to go out from the loop and I'm going to print I guess print guesses. I don't know why he's going for a string. Yeah, print my answer. I'm going to do this. Let's build it. And it's not stopping. Why? I have no idea. Did I miss something? Yeah, well, actually, it's 25. I did change the code. I know that I did change the code, but I did not change it a lot. I change it like I can deal with it. Well, here have to do break now, right now. So break. Failed. Yup. But 13 is not the square root of. What did I do wrong? What did I do wrong? Um, I don't know. Wait, let's see him how he.
Capacitor's too small. I'll bring the low range down into
So I'm going to watch him how do he run the code to see.
there, and I keep sorting it down until I get into something that's reasonable. This algorithm just captured that idea I just described. So let's try it out. We'll do it with 25. Here's a bisection search on square root, and if I run this code, wow, it actually got there very quickly. It did it in 13 guesses. I'll remind you, in the previous case, we took 30,000 guesses to get there. I don't want to print all that out on my screen. And notice how quickly it zeroes in. It starts off with low, 0, and high.
So he, he want to print all this. I don't want to print all these. My code did print actually. Uh-huh. Did I do something wrong? Yeah. Why in the hell low is 1? Why in the hell low is 1? Yeah, this is... He did write it. Yeah, I'm going to write it 0. I'm sorry. So 0.0, and I'm going to build my code. There is something wrong with Mary. 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 Low is my answer.
Root, and if I run this code,
I don't like to write the same code. Maybe if I just take out the break, I'll try to build. So it's not stopping. Yeah, okay. The problem of my code. So this is just printing stuff, you know, like it's nothing. My other operations are the same. the output is yeah. So in my case it's stopping, but the answer for me, my answer is always high low divided by 2. So high and low divided by 2. Yeah. Why this is not working? So divide by 2, it's a 2.5, but it's not continuing the process because of maybe like this, because we do this. Let's try to build it. No, not working. Always not working. Actually, I do not understand, because so let's go through it. So x is 25, option is 0.01, the answer is 0, high is x, and low is 0. Okay, so high plus low divided by 2.0. Maybe the spaces, or so y, the absolute value of my answer, the square root of my answer minus x is bigger or equals to epsilon. Okay, print, this is just printing stuff. There's no, because like, let's do a new let's say x equals to, let's save it as test on my desktop, test, please. So it's no. We're going to say x equals to 2, print, yeah, x equals to 2, print actually let's do this, 25 high is equals to x, low equals to 0 point, I'm sorry, 0.0, and let's do the same here, and my answer is let's say print string my answer. So it's the same thing what I'm trying to say, but it's just not, it's not looping, you know. It's just not looping. Why it's not looping? I'm not, I don't know. So
very quickly. It did it in 13 guesses. I'll remind you, in the previous case, we took 30,000 guesses to get there. I don't want to print all that out on my screen. And notice how quickly it zeroes in. It starts off with low 0 and high 25. And then it says low 0 and high 12.5. And then low 0 and high 6.5. You can see if you look at the printout how quickly it narrows in on the range. That's really cool. Okay? Do the same thing with cube root. I can do exactly.
I don't want to do the same thing with cube root. There's something wrong. So it's why it's not
Change the-
working. Shit. Stop. Okay. Stop. No, Control O. First. Yeah, please, can you stop? I hate when it does this. Okay, so I will try to write the same exact things that he wrote. No. So yeah, I did lost my. Where is it? Yeah, let's see. Let's do the exact same thing.
The low part of the range?
Please shut up a little bit. I'm very bad. Don't listen to me. Don't watch my YouTube, guys. I'm very bad at this. So let's see. Am I recording right? Yeah, you can see everything. Yeah, okay. So go back. Okay. So until now, everything is until the while loops. The absolute value of everything. Okay. Now print maybe here it's because of this. Maybe on. No, you can't add. Yeah, okay, I know. Ah, nothing. So, we did say that we are going to say low equals low equal plus string of low plus height plus string of height plus I think my answer. My answer. Answer plus string. Yeah, okay. So I am going to do here a break. So just I'm going to test break. Okay. So after that, I think everything is the same. Guesses +1 if uh-huh. But the thing it's wrong. I don't. Wait. Is it my code writing? Let's have my answer. Okay. Else, let's have my answer. Here, sorry. Okay. And not getting it. Is this the else of I literally did the same. That's very bad. I don't know how to respond. Why it's going on with me?
Answer is too small, I bring the low range down into there, and I keep sorting it down until I get into something that's reasonable. This algorithm there very quickly.
High, low, high, low, high. It's the same thing. Divided by 2. I don't get it. Why? So until it will always be bigger or so that the condition here is it's the same thing. It's the same thing. I have no changes whatsoever, except that is my answer. Oh, please. Ah. 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 Well. That's very bad. I am very bad. I suck. This is suck. I hate programming. I hate programming. I literally hate programming. Fuck that shit. Dude. Oh. I'm literally exhausted. You know? Literally exhausted. Why? Why? This is why I. Ah! Finally! I'm sorry, guys. It's really bad. It's been hour and a half. I'm going to continue this video, and I'm going to call it off. I don't know if. Yeah, wait. How much videos left? 1, 2, 3. Yeah, I'm going. I'm calling it off. I will do the next one in the evening. I want to sleep. I'm literally tired. You know, exhausted. Yeah, I'm going to take this also. Let's go.
You did it in 13 guesses. I'll remind you, in the previous case, we took 30,000 guesses to get there. I don't want to print all that out on my screen. And notice how quickly it zeroes in. It starts off with low 0 and high 25. And then it says low 0 and high 12.5. And then low 0 and high 6.5. You can see if you look at the printout how quickly it narrows in on the range. That's really cool. Okay? Do the same thing with cube root. I can do exactly the same idea. This is almost exactly the same code. The only difference is I'm using guess cubed rather than guess squared. And I'm going to keep track of otherwise exactly the same information. And let's compare that. If I go over and pull up my cube root example, we'll start with 27.
So what do you think, guys? Should I do it? No, actually, it's the same thing, but you just changed it for 3, right? Yeah, I do think so. Let's try it. Yeah, it's just 3 here. I hope it's just 3. 3. And yep. Right, F low, high guess, title low. Yeah, this is it. But it's just he moved the count 1 from here to here, and this stays. Yeah, so it's the same. Let's do it. For 25, he did it for how much?
And I'll remind you that in this case I was doing 30,000 checks to deal with it.
27. Let's do it for 27. Yeah. 27. Capital S, capital B, and it should be 3. Yeah, it's 3.
Now I run it, and in 14 guesses it gives me a really good answer. And if I pick something that's not a perfect cube, like 54, and I do the same thing, in this case it took 15 guesses to get me a really good answer. This is a powerful tool. That idea of bisection search, throwing away half the possible values at every stage, lets me very quickly zero in. As before, I can ask, well, can I do everything? This is only going to work for numbers bigger than 1. What about fractions? Well, I know with fractions between 0 and 1, now the difference is that the root doesn't lie between the number and x itself, or it lies between 0 and that number. But that's an easy ways to change, and we could actually think about making that change. But just to remind you of how powerful this is, notice what happens. If I start up with the number n, on the first guess, I reduce the set of things in half. On the second guess, I reduce it by another half, so it's now n over 4. After g guesses, I've got a range that's only n over 2 to the g. And what this says is that in an amount of time that is going to grow as the log of n, I'm going to get to an answer That's really nice because it says I don't take linear time, I actually take less than linear time to get there. We'll come back to that idea later on in the course, but this is a great example of a logarithmic time algorithm finding an answer very quickly. I jumped ahead a little bit because I already started talking about what happens if I want to look for cubes only greater than 1. I could modify it to look at negative cubes, and I could modify it to look at things where the answer is less than 1. And so, for example, if x is less than 1, I just change the search space. So now, rather than going from 1 up to x, it goes from 0 to x. Rather than going from 0 to x, I want to go from x up to 1. I'm not going to do it. I'm going to leave it for something you to try out, but it's really easy to make that change. And again, notice what I've done. Start with the basic set of code, check to see what it runs on, and then decide if I wanted to use the same code, how could small changes have it run on other kinds of solutions.
Okay, so let's try this rapidly. So we are going to do 0.4. Let's run it. Holy crap. Because I did, yeah, let's do break here. Okay. Because it's 4. 2 square roots. I need to square root, not the cube root. Let's take this off and let's do build. And it is still not working. Okay, why? Break. Build. Huh, because low is 0, high is x, and well, I don't know. How much is 0.2? Yeah, let's search for calculator. So I don't know what's 0.2. What is this? Hold on, standard. 0.2. 0.2. So 0.04. So okay, let's try 0.04. Let's do one. So it's going to do build. Yeah, I don't know. I'm not in the mood to find the solution. Actually, I'm going to keep this and I'm going to do a comment here saying so the comment is how do we call this? Hashtag square root. Algorithm. Save and close.
What can I take away from this? Bisection search really radically reduces computation time. I went from 30,000 times through a loop to 10 or 15 times through a loop. That's really nice. And this should work on any problem with what we would call an ordering property. That is, the value of the function being solved varies monotonically. That is, it increases as the input value increases. G squared has that property. As I change G, it grows. G squared grows as G grows. G cubed, same kind of idea. So bisection search will work on any problem that has that kind of property. We're going to see more examples of that as we go through the course.
Yeah, that's it. So this is. Sorry, we could not search this. Okay. So just going to check this. How much?
In an example.
So it's 9 minutes, and this one is
Generalized.
5 minutes. What do you think, guys? Do you think we should do it or not? Whoa, 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 whoa! What did just happen? Ah, my screen is off. Okay, wait. Sorry. Yep. No. This is here. And yeah, I think we're good now. Yeah. So, we have this and this. What do you think, guys? Should we do it? Yeah, what the hell? Let's do it. Actually, I'm hungry. Again. Why? Okay. Refresh. Have no internet. Yes, I do. Yeah, thank you. That one really did. It was very bad. This one was. That's annoying me a lot. So I'm going to take this. Yeah. Last time. Shut up. Yeah, I have no idea why it's doing this. Did I change anything? Yeah. No. What was this? What was this? What was this one? Yeah, because yeah. So 25 belt. Nice. So I'm going to save it like this. Save, and now we are going to go to test. Yeah, this one. So if I need to write something, I will write it here. So let's do it. Let's do it.
In an example of an algorithm that computes floating point numbers as an answer. And we've been playing with floats earlier on. I now want to take a little sidetrack to talk about floats and how they're represented inside the computer. And in particular, you may have experienced earlier on in the course, where you'll get answers that'll give you some funny number where you're expecting 3.0 and it gives you 3.0000125 or something else. To deal with this, we need to go inside the machine for a second and talk about how floats represent real numbers. They certainly approximate them, but it's useful to get a sense of how the machine actually stores it, because it can't store an infinite number of decimal points or digits after the decimal point inside the machine. Here's the basic idea. Let's start with a decimal number, the numbers you're used to dealing with. The number 302 is really 3 times 10 squared plus 0 times 10 to the first power plus 2 times 10 to the 0th power, or 1. It's 300 plus 0 tens plus 2 ones. Binary numbers, which is how the computer stores things, are actually represented the same way, but now in terms of powers of 2. So the number 10011 in binary is 1 times 2 to the 4th plus 0 times 2 cubed plus 0 times 2 squared plus 1 times 2 to the 1 plus 1 times 2 to the 0. Which is actually 16 plus 2 plus 1, or 19, in decimal notation. Internally, the computer represents every number in binary, whether it's an integer or it's a float. How would we use that idea to think about how do we represent floating point numbers? Well, let's think about how we could convert a decimal integer into a binary representation, and then we'll do the fraction portion of it. So given a decimal integer, how would we convert it to binary? Well, let's take an example. My example would be the one I just had before. 19 in decimal is 10011 in binary. If I had 19 or anything that represents that number, how could I get it out? Well, what I can do is the following little trick. I can take the remainder of that number relative to 2. And that remainder actually gives me the last binary bit. It'll give me this bit right here, because that's the remainder that's left when I divide by 2. If I then take x and divide it by 2, integer-wise, using that double slash idea, all of the bits get shifted right. That is, x double divide by 2 is now 1 times 2 to the third rather than 2 to the fourth, plus 0 times 2 squared rather than 2 to the third, plus 0 times 2 to the 1 rather than 2 squared, plus 1 times 2 to the 0 rather than 2 to the 1. Or another way of saying it is, notice I've taken these digits and just shifted them to the right. If I keep doing successive divisions like this, I can keep track of each of the bits that comes out, because the remainder gives me the next bit, and when I'm done with all of that, I've converted to binary form.
What?
So basic idea, given an integer, take the remainder with respect to 2, that's the low order bit, divide integer-wise by 2, shifts right, do the same thing until I've exhausted the entire integer representation. So here's a little piece of code that would do exactly that. Right? If the number's less than 0, I'm going to put on a flag that says it's negative, and I'm going to use the positive version of it by taking the absolute value of that number. Otherwise, I'm going to put in a flag that says it's not. And then I'm going to simply accumulate those results. If the number is equal to 0, it's just 0. That's pretty obvious. Otherwise, as long as the number is greater than 0, I'm going to do remainder, add that in, because that's the next bit into result, do the division to shift it to the right, and keep going. So if I look at that, here's a simple example of doing that conversion, converting decimal to binary. I'll start with a real simple example.
What the
If
fuck?
I start off with number as 3, and I do that computation, it didn't print anything, but the result is sitting in result. And there I get it. The binary representation of 3 is not surprisingly 1 plus 2. Let's just check to make sure I wasn't misleading you when I said 19 was, in fact, what I claimed it was. So if I make it 19 and I run it and I look at result, it gives me back 10011, exactly as I said. All right, cool. So I can take integers and convert them into binary. But I started talking about floats. So how do I deal with the fraction part of this? Well, I can do almost the same thing.
I
Let's
have
take an
no
example.
idea what just happened.
3/8 is 0.375, and in binary, that is 3 times 10 to the minus 1, plus 7 times 10 to the minus 2, plus 5 times 10 to the minus 3.
Yeah, actually, I'm tired. I'll call it off for now, and I will try in the evening to see if I can do it. I have to take some rest. Actually, I'm sorry, guys. As usual, I'll upload this now, add it to this playlist, and yeah. Hope you. Actually, that was really bad today. I'm sorry for yelling, but I'm tired. I'm sorry. Yeah. See you next time, guys. Have a great learning journey. Bye bye.